Welcome back to Building Janky Programs. Today we're going to be talking a little bit about searching, sorting, and time complexity. I'm joined today by Professor Philip Faulkner. How you doing?
Doing swell.
All righty. So a good place to start is talking about this big O notation. Um, Professor, do you know where the N originates from by chance?
So like big O of N or whatever.
Yeah,
Yeah.
like YN.
Yeah. So in mathematics and physics, typically, the capital letter N is like it's the number of something, so like maybe it's the number of molecules in a gas or that kind of a thing. So it's just a number, just means how many of a thing you have, capital N. Yeah.
Yeah. So N is referring to size. Um, so for example, if I was gonna say print something out, whoops, if I was going to print out hello, what is the time complexity of this?
What is the
Well,
time? Yeah.
what's my size, right? What's it referring to? Well, here we can say that size is referring to the number of things happening. And in that case, it's O of something, right? Something's happening. Is it varying? No, so it's constant. Okay. So here we can say that the big O of some constant C is equivalent to big O of 1, right? Where we don't care. The time complexity, there's not a time, or there's not a space change, there's not a size change, and so therefore any big O of some constant is going to just be big O of 1. That makes sense?
Yeah, I think so. Hopefully it
Okay.
makes sense. Yeah.
So in order to make this sound a bit or more followable, let's have some integer n here. Um, so now we can start exploring different uh, big O complexities. So while I is less than n, I'm going to do I plus plus. And then here, I'm going to have this same line that I had before, this print hello. Okay. So now what's the big O? Well, we have some n variable, right, which is 10. And so every time I call this for loop, what's going to happen is it's going to print hello 10 times. Okay, well, n is 10, 10's a constant, so big O of 1, right? Well, no, because it's a variable, right? So if I have n is 15 now, well, that just changed how many times that ran. Um, Similarly, we can think of this as big O of n because every single time that n does change, the amount of time it takes is linear, right? We have some, if n is 5, it's going to run half as fast as if n was 10. Or if n is 10 and then I make it 20, that's going to take twice as long. Does that make sense?
So so to do a single println statement, let's say that takes 1 unit of time. And so, but now you're going to try to print it out 10 times. So it takes 10 units of time. But if you print it out 20 times, it takes 20 units of time. So by doubling little n, you're doubling the amount of time that the program takes to run.
Yes. All right. So we talk uh, big O of 1, big O of n. What's some other things? Well, we can think of quadratic, right? So big O of n squared, what does that look like? So it looks pretty similar to what we had before. We have some int I, while I is less than n, I plus plus. Now let's nest another loop in here. So for int j is 0, while j is less than n, j plus plus. And then we'll have this print line, dot println, hello. Oops. Okay. So here we can see that ran quite a bit of times. If I make n be 3, that should run 9 times. And here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool, cool. So here, n is 3, but it ran 9 things, right? If I increase this n to 4, well, that would mean it's now 4 to the 2, right? Which is 16 times. So each time you increment, it's going to be n squared more times or more. Am I explaining this okay?
Yeah. So, yep. So whatever little n is, then the amount of time that it takes is going to be that number squared. So if you, for instance, double n, that's 2 times as big. So 2 squared is 4. So it's going to take 4 times as long. If you triple the size of n, 3 squared is 9. So it's going to take 9 times as long, etc. So every time you're kind of doing some multiple of little n, you're squaring that multiple. So if you're doubling it, you're taking up 4 times as the time. If you're tripling it, it takes 9 times the time, etc. Really good example. And again, I come from a physics background, but we use like 2-dimensional arrays all the time to kind of represent like something. Maybe it's what's a good example? I don't know. It could be like maybe a piece of metal, right? And then there's electrons inside of there moving around. You want to model the current, the electrical current through this piece of metal. And you represent it by a 2-dimensional array, and then you have to calculate certain stuff at every single point. Is there an electron there? What are the forces on it, etc. And so you have to do this across this 2-dimensional array, X and Y. And so you end up doing a nested loop just like this. So you loop through each column, and then you go row by row, and you do all these calculations on this 2-dimensional array. Now, if you double the size of the piece of metal, so if you double your computational zone, since it's kind of this area, right? You actually increase the computational time by a factor of 4. If you triple the size of your space, then the computation time goes up by a factor of 9. So it's n squared, and that's really bad. And typically, when you're modeling something, right, you want to have really high resolution to get like really precise kind of numbers or calculations. It's just like if you have like a 12 megapixel camera versus a 50 megapixel camera, right? The 50 megapixels is going to have a lot more resolution, finer detail. And most of these types of problems, when you're dealing with these nested for loops like that, yeah, it's n squared, and it gets computationally heavy very fast. I mean, imagine if you are working on a 10 by 10 grid, and then you go to a 100 by 100. So you're multiplying that by 10 squared, that's 100 times longer, just to increase it.
Yeah, absolutely. I think that's a great explanation. Let's talk about how we can use this to our advantage when we're programming. So let's say, for example, we had another for loop here. It's the same as the first loop. And then we're going to see, okay, what's the big N of this entire thing? Right. So we have some for loop here, and we're going to print out, system.out.println, some hello text. So here we have this top for loop, which is running in O of n time. And we have this nested for loop that's running in O of n squared time. So what could we call this? Do we say that it's, big O of n plus n squared? You could, right? But you could also think of it as, okay, what if I also had another line in here, right? I had some system.out.println hello one more time, right? This is getting more complex as I keep on going and going and going. And I mean, you could write this all out, but do I really care that much? This n, is it really going to affect my time as much as this n squared, right? So say if n's 100, well, 100 squared So 10,000, is that going to affect it a lot more than 100? Absolutely. And then this one, right? This it's so small at this scale, it doesn't even matter. So with that being said, we can just express this as O of n squared. There are some pitfalls in this though. So let's go ahead and run this. Okay, cool. We got our output. So if I had a for loop, right, and then this for loop is going to run 10 times, what would be the big O of that? So if I, not in a for loop, but I separately took this for loop and I ran it 10 times. Let's do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's the big O of that? Well, you could say it's 10n, right?
Gotcha. I see where you're going now. Yeah.
And if n is 10, then yeah, it's n squared, right? But when n increases, that 10 stays the same, right? And again, that 10,000 versus 10, the 10 doesn't even matter anymore, right? So we just express that as O of n. So that makes it so if you have a nested loop, right, and n is 3. So if you had some nested for loop here, like we have right here, the second one, and n is 3, and n is 3, right? So that runs 9 times versus if I had 3 different for loops that ran 3 times. One of them's big O of n, one of them's big O of n squared. And that has to do with how much does it change when n changes, not necessarily the current data set. Does that make sense?
I think so. So, so first of all, when we're talking about these O of n, these complexity things, yeah, we typically are interested in the so-called asymptotic behavior of the algorithm. Now, for small data sets, for small sizes, sometimes you might have the O of n is kind of on the same order as O of n squared. I'm thinking of like a graph, right? If you just graphed like a straight line and then you graphed a parabola, right? At certain point they intersect, and then the parabola is going to take off way faster than the straight line. But there's a certain, for small n, that straight line is actually a little bit better, right, than the parabolic. So for small n, it doesn't matter. But as n starts getting really, really big, so the asymptotic behavior, that's what's going to ultimately end up dominating. So in your example, if you had n squared and it's 100, that's 10,000. And if you're just adding a constant to that, the difference between 10,000 and 10,001 is nothing, right? So we don't even worry about the little one. And if it's just n, right, for 100, even 10,000, 100 is just 10% of that. I mean, so by the time you're getting up to a million or a trillion, whatever kind of size data sets, yeah, the n just doesn't matter anymore. And then I think the other thing that you were mentioning was if you ran that O of n loop, there's the single for loop. If you ran it 10 times, now you're taking the O of n and you're multiplying by some constant. So you could take, so big O of n, maybe it's like some little number c, some constant, whether it's 10 or 3 or whatever. And typically we drop those constants off either also, right? Because that little constant multiplied by an n squared, yeah, we just don't even worry about the constant. And so we just still call it n or n squared. So yeah, I think it's, again, in all of these cases, it's kind of, we're interested in the asymptotic, like for very large n, what does the algorithm look like?
Yeah. And then in the same way with the constants, if you have like, say, 2 size variables, the one you focus on matters on which one's bigger, right? In the same way, right? So if you have some X variable and Y variable that's changing, well, which one's bigger at the time? Because that one's going to have way higher precedence than the other. And so that's a really, you come across that question a lot, is what is n? And most of the time, if you're working with an array or some other structure, you have a size. And so you can assume that that's your n. But it's not always so clear, right? If I hard code in this 10 here, you can think of it as a constant, or if it's changing, you can think of it as a you can think of it as a variable. And that really just depends on the case, right? So being able to recognize that, hey, this 10 is a constant, right? So then it ran that 10 n times, right? And then we can throw out the 10.
Yeah. Right on. I like it. Yeah. So this would be a O of 10n, what this nested for loop right here. Yeah. Cool. And so we would just drop the 10. We would still call it an O of n algorithm. Yeah.
Mhm.
Yeah. Pretty cool. Pretty cool. And yeah, I guess it's, this is in the chapter 13 of our textbook, and that's also talking about searching and sorting. And so, yeah, you have a lot of times you have a large data set, and you want to find something inside of there. And so you got to search through that data set. There's different algorithms that are going to have different levels of complexity. And the kind of the size of your data set would be the n, right? And there's let's say you have a data set and you're just going to search through it once. I'm only going to search through it once. So then you could just use like a sequential algorithm. You could just go one by one through the whole thing. And then you find your value, whatever it is you're looking for, and then you report it and you're done. But let's say you have a data set and so that would be like O of n, right? O of n times. So if you double the size of your data set, it's going to take you twice as long. The worst case, it's going to take you twice as long to get through it. If you triple it, it's going to take 3 times as long, just because it's 3 times as big. However, you could sort your data set first. Then you can take advantage of being able to search through it more efficiently. So you could reduce the amount of time that it takes to actually search through a sorted data set. The problem is that it takes time to sort it in the first place. So if you know that you're going to be searching a data set a lot, so think of like a search engine like Google or something like that, then it's worthwhile to spend that extra time to get everything sorted, because once it's sorted, then you're able to search through it much more efficiently. And so then we start getting into like weird, O of n log n, or those kinds of things, where we're kind of combining different things together and getting these more complex kind of complexities.
Yeah. And one of the things, you can always linear search, right? You can linear search through anything and find that. But as you're saying, right, as you double that size, you can think of that linear search as O of n. Anytime you double that size, it's going to take twice as long. It's going to take 3 times as long. So looking at some search algorithms, right? For example, this one we'll put in the description. You might see some of these big O times and think, well, when is that ever going to be helpful to me, right? For example, you can look at this bubble sort algorithm. It shows a little animation on how that happens. Here, its worst case is O of n squared. So you might look at that and go, well, I'll just do a linear search every time, right? Because that worst case is always going to be O of n. Well, there's different use cases where that's actually way faster than using a linear search, right? Your average case is going to be this n times log n, right? And then that's for sorting, not searching, my bad. So when you go in and you sort your data, when you search it, right, then you can base values off one another. So like, for example, binary search, something we talk about. You can compare values, see which one's less than or greater than, and you don't have to look at everything, right? If you have a sorted list and I'm trying to find 5, and then I just like pick some spot, I look at it, if I look at it halfway, I'm looking at 5 and 6. Well, 5 is what I'm looking for, so let's grab that, right? Or if, you can look at different parts where it's likely to be when it's sorted. So that way you're not having to go through an unsorted set, right? And I think that's what you were saying mainly is that, you know, you can, if you're going to be searching through it a bunch, having it happen in n time every single time is yeah, it's not gonna be
Yeah.
great for your program.
So for instance, if your data set is sorted and you're doing a binary search, so then you know, a linear search or a sequential search would be O of n, but a binary search would be O of log n. So that means if you increase your data set by a factor of 10, it only takes twice as long instead of 10 times as long, right? If you increase it by a factor of 100, then it takes, I'm sorry, increase by a factor of 10, then it takes, wait, twice as long? Yeah, I don't know. 3 times, powers of 10, right? Because it's logarithmic. So, so whereas a linear, if you go up by a factor of 100, you know, it takes 100 times as long, but the log of 100 is 2, so it only takes twice as long for a binary search. So you end up doing log of n time for good kind of algorithms, you know, log of n or n log of n to sort it first. So you're spending that extra time, that extra complexity, but once you have it sorted, now you can save a lot of time on your searches.
Yeah, I think the base in big O notation is always 2,
Yeah, that's right.
but
Yeah.
yeah, so one way that I use to spot that is if it's dividing by 2 every single time. If you're
Yeah.
like iterating through something and it's consistently dividing by 2 each and every single time, that's log of n, right?
Yeah.
And then similarly, if it's doubling, that's n squared.
So I think a common way that's called is
Yeah.
like it's a divide and conquer algorithm. So you're taking your problem and you're dividing it into a problem that's half the size. Then you take that problem, divide it into half the size, and then half the size. And so yeah, it's log base 2 of n. Yeah, pretty sweet.
Yeah.
How about I'm looking at the textbook here, 2 to the n, 2 to the n. What kind of a algorithm is that? I think.
Well, that's the what do you say, the exact opposite of log,
Yeah.
where it's doubling every single time.
Yeah. Yeah.
And
Yeah.
yeah, a good example is the Fibonacci one, right?
I think so. Yeah. I think Fibonacci is 2 to the n. Yeah.
So if we take a look here, and I think we did this one in a previous episode, you look at, you know, some Fibonacci method and you say, you know, if n is less than or equal to 1, we'll just return 1. And then otherwise we will return fib of n minus 1 plus fib of n minus 2. Close that off. Okay, cool. So now if I say fib 5, I get 8. That's correct, I think, right? Or is it 1 off?
It might be 1 off. I'm not sure. I have to think through it too. So that would be 6. It depends. Some people start at 0. Some people start at 1. Either way, I think it will be off by just a little bit, but not a biggie.
Right. Well, here we're just talking about, you know, the complexity. Yeah. So if we look at it, let's see, fib of I or fib of I. Okay, yeah, that's close enough. Anyway, so yeah, so we can look at this fib method here. So every single time we're calling this fib n minus 1, right? That's pretty much just O of n, right? Because we're going through and we're going to go through the entire thing once again. And we're going to go through the entire thing once again. And the entire thing is just one thing, right? It's this addition here. And then similar thing for fib of n minus 2. So when you trace this, it actually branches off into 2 separate calls every single time, right? You can, yeah, I don't have my pen on me, but yeah, fib of n minus 1 will call fib of n minus 2 plus fib of n minus 3 relatively, right? And so that'll keep going until it hits a base case. Well, that means that, you know, this first call is calling 2 things, then the next one's calling 4 things, and then the next one's calling 8 things, and then 16 things. and then you might think a little bit and you go, oh wait, that's 2 to the n, right? So yeah, that would be the opposite of the
So break it,
log
man.
base 2.
Break it. Do fib of like, I don't know, 50.
I think it actually caps off at like 43.
Oh, really?
Yeah. Yeah.
So 44 is going to break it. That's when you,
I think that's when it overflows.
that's when it overflows. Right on. But,
Oh,
ooh,
no.
you got it. It's definitely taking longer. Like I can just feel
Oh,
it.
yeah.
Yeah. Jeez.
Yeah. So if you think about it, right, we have this 2 to the n, right? So if we do math.pow 2 to the 45, get an idea, that's how many times this is running,
Yeah. So it's a
right?
3.5 with 13, move the decimal place 13 times. So 10 to the, let's see, 10 to the 9 is mega. And then 10 to the 12 is, no, wait, mega is 10 to the 6, 10 to the 9 is giga, 10 to the 12 is tera. So we're talking like whatever, tera. It's a lot.
Yeah. Really big number.
Yeah. Yeah.
So this is why the big O is necessary, right? Because we can measure that. We can say, okay, given this and whatever hardware we're running can run this many things in this amount of time, we can estimate how long that runtime is going to be. Without that data, I can't give you that off the top of my head. And that's on my machine, right? But it's a tool that we can use to measure complexity of different kinds of algorithms. And so that's super useful to us.
Usually try to avoid 2 to the n. Any kind of
Oh, yeah.
exponential, yeah, even quadratic. Sometimes quadratic you can't get away from it, or even cubic. So n cubed. Sometimes you just can't get away from it. And in a lot of my physics modeling simulations that I did, yeah, there's kind of clever ways, little tricks you can do, but I had algorithms that would, I had some stuff that would take like a week to run on my computer. But then I got it onto the supercomputer and it took like a couple minutes, which was awesome. And so then once I did that, I was able to increase my problem space. But yeah, there's oftentimes you'll get into some algorithms where it's like it's going to take a year to run, and then obviously that's just not, most people don't want to wait a year to get their results. You know what I mean? So yeah, or maybe it's like even the age of the universe or something. It's just impossible. You can never do that algorithm. So
Yeah, and these days you don't have that big of an issue with that. Things can run. It just ran this real big 13-0 number times in less than 10 seconds or whatever.
yeah.
So a lot of the time you might think to yourself, well, I don't really, this n squared doesn't really bother me, right? Because there's not much of a time difference, and there's something to be said about that. But your program might not be running on your computer every single time, or for example, like Professor Philip mentioned, you got Google, right? It's giving you billions of results in fractions of seconds and constantly being updated and optimized to do that much things on that many, this huge n size. Is an important thing to take into account.
Yeah, for sure. It depends on your problem, because like you could also think about like sorting, like a selection sort or an insertion sort or something like that. I think is what, O of n, I think, or is it O of n squared?
Selection sort
I think it's O of n squared.
n times
Yeah.
n squared. Yeah.
So like O of n squared, which might sound bad. And then like, for instance, the merge sort, I think is n log n. But for small data sets, actually the selection sort is a little bit faster than the merge sort. But again, the asymptotic behavior, if your data set's starting to get really, really big, then the merge sort is going to eventually take over selection sort. And you definitely don't want to try to do like a selection sort on a huge data set. You want to do something like a merge sort. But yeah, so it totally depends on what your use case is. In some cases, maybe O of n squared is preferable than an n log n or something. So
Yeah,
and I
yeah,
think a
'cause-
lot, I think a lot of computer engineers or software engineers, they use like a hybrid approach. So they'll use a merge sort until the data sets get small enough, and then they'll switch over to a selection sort. And then when you work backward, then it goes back to the merge sort. So there's kind of like a hybrid technique to try to take advantage of both, the advantages of both.
Oh yeah, totally. I think even ArrayList has like this initial capacity in its constructor where you can like set its size. If you have like a really big, or a really large amount of data, that's going to go in. You can make that, because it would do O of n to expand a couple of times, and so you can just make that O of n, one time, which big of n either way, right? But we know that that's a lot faster, right? When you set that initial capacity manually.
Right on.
Yeah, totally. But knowing your data set is super useful, and switching those algorithms and doing all that. Absolutely. Yeah. So this link we'll put in the description. It has a bunch of use cases for each of these, which is, useful to know. It's also got, these animations showing you how exactly this works and then a little code snippet. It is in C++, I believe. But what you'll notice about pretty much all C-based languages, especially, you can probably read this just fine.
Yeah.
It's just Java.
The Geeks for Geeks has Java versions. Yeah, you can
Mhm.
just Google it and it's all over the place. Do you want to do that one table thing that you
Oh,
showed me
yeah.
last time?
Yeah, let's take a look at that. Let me go ahead.
Got the
and
link
pull
handy
that
here.
up. Oh yeah,
Just put it in the chat.
thanks. Okay. Yeah, so here we can see all these sorting algorithms and then a little animation on how each happens. And the fastest
So,
one here is
Bubble.
actually,
Yeah. So Bubble finished the fastest on nearly. Wow. Selection sorts taken forever. Yeah. It's pretty
yeah.
cool. Yeah.
So insertion and selection sort are super similar, but this nearly sorted insertion was actually the fastest out of all of them.
Yeah.
Even though insertion has a worst case of n squared, well, this just happens to be the best case out of all of them, right? Boom, it's done. So yeah, this gives a great illustration of how different data performs differently, and so you can't just say that this one's faster than everything else, right? There's always going to be that case where one's better than the other, and that's why there's so many.
Incidentally, if you wanted to do so, it's where it says nearly sorted, if it was nearly reverse sorted, then the selection sort would win because of the way the algorithm is set up, right? Yeah. Yeah.
Yeah, know your data, right?
Yeah.
Yeah, absolutely. So this is probably this takes forever for selection sort. Yeah.
Yeah. So, okay. So I think they're still sorting in reverse, but yeah, it'd have to be nearly sorted in reverse. Then selection sort would work.
Yeah.
Yeah. All right, man. I don't know. Are we done?
Yeah. Yeah. I think that we covered everything that's important.
Cool. Like and subscribe, I think. I don't know. Yeah.
Hit that bell.
All right. See you all.